Hello everybody. So now in last video in vector analysis we discussed about the scalar fields and vector fields. Now let us discuss about the gradient of a scalar field. So now what is the gradient of scalar field? When del operator operates on a scalar function pi x comma y comma z, then we call it as gradient of scalar field, right? We are denoting with pi, okay? We call it as grad pi is equal to del pi. In such a way we will write, right? When del is operated on scalar function pi, we call it as gradient of a scalar field, and we write it as grad pi. That gradient pi is equal to del pi. Del is an operator. The operator is I dou by dou x plus j dou by dou y plus k dou by dou z, right? So now the grad pi is written as I dou by dou x plus j dou by dou y plus k dou by dou z into pi. So this is written as I dou pi by dou x multiply plus j dou pi by dou y plus k dou pi by dou z. So in such a way, we will write the gradient of scalar field. Alright? So now, let us go for the formula for gradient of a scalar field. Alright? For finding the formula, here I am considering two surfaces, one S1, other S2, very closer to each other. Let the surface area of S1 be S. Now the surface area of S2 be S plus ds, right? This is, the area is somewhat greater than, S2 is greater than S1 in such a way. So this is S and this is S plus ds, right? I'm considering a point O here. I'm considering 2 points, one A, other B, on surfaces S1 and S2. Let the distance from O to A, or the position vector, let it be R. And here from O to B, so it becomes R plus dr, right? So now, what will be the AB? AB will be equal to OB, sorry, scalar, no? OB minus OA, R plus dr minus R, that is equal to dr, right? Now from A, I am drawing a outward normal end from A, from surface S1, from point A, I am drawing an outward normal N, right? Now, the distance between this outward normal B, I am placing a point C here. Now, this AC becomes the minimum distance between the two surfaces. Let us denote that distance with dn. Now, here you see, I will write dr this side. There an angle is formed here. So, now first point, the rate of increase of S in first AB direction. What we will write? Increase of S, dou S by In AB direction, the distance from A to B is dou R. Similarly, the rate of increase of S in AC direction, the least distance or minimum distance is dou N. So, dou S by dou N. Right? Now, next, from triangle, you see here triangle is forming. ABC triangle with angle theta. So, from triangle ABC, cos theta is equal to adjacent side by hypotenuse. So, cos theta is equal to what is the adjacent side? AC. What is the hypotenuse? AB. Right? That is cos theta. What is AC? dN. What is AB? dr. Or dou N, dou R. So, dou N is equal to dou R cos theta. Now, let us substitute this here. Dou S by dou N. In place of dou N, dou S by dou R cos theta. I am bringing cos theta to this side. What I will get? Dou S by dou R. Dou S by dou R. Cos theta I am bringing to this side. So, dou S by dou N into cos theta. Now, if theta is equal to 0, cos theta is equal to cos 0 equal to what happens? 1. Means dou S by dou R is equal to dou S by dou N. If theta is equal to 90, cos 90, 0. So, comparing these two, when we get the maximum value, when cos theta is equal to 1, we are getting maximum value. When cos theta is equal to 1, we are getting, when cos theta is equal to, here theta is equal to 0. When theta is equal to 0, we are getting maximum value. That we can say maximum rate of increase of surfaces. Right? When theta is equal to 0, we are getting the maximum rate of increase of surfaces with unit vector n along it. So now this becomes, what is dou S by dou N I said? Here rate of increase of S in AC direction. So from this we are understanding that in magnitude and direction, the rate of, in magnitude, the rate of increase of this S is along AC direction. Right? Along AC direction. So this dou S by dou N, we call it as gradient of scalar field. Right? This we call it as a gradient of scalar field. So as the maximum rate of increase is in direction of AC, we term this as a gradient of scalar field.